So I'm now going to measure this at 8 different positions. We really want to see very accurately what this bore is like, so that when we machine our axle tubes, we have something that is just the right fit. So I'm aiming for like something around 1,000 of an inch interference exactly, and that gives me the dimensional stability as defined in Shigley as being optimal for an interference fit. This isn't exactly round, so I want the smallest amount of interference that Shigley specifies, because I've got to add to that the non-roundness of this opening, and that's how much it has to shrink when I cool the axle shafts to fit them in. So that extra interference as a result of the non-roundness means that I have to heat this up hotter and make the axle tubes cooler in order to fit. And I'm planning to actually heat this up with a regular gas torch, and then actually cool the axle tube with dry ice. And the dry ice should make it cool enough and this hot enough that the delta between the temperature gives me 2 or even 3 thousandths of an inch clearance that I need as a result of the non-roundness. But after it expands, the actual interference is probably going to be 1,000 inch, and that's what I'm aiming for. So it's a bit of a tricky, unusual engineering project because this is oval and not round. So let's see whether we can get a bunch of measurements on here. So I put markings going all the way around. So let's see what that gives me. Two four nine eight eight. 24988. So I did calibrate this before I started. Two 5007. Now we're going to do 45 degrees. 24983. 24983. Okay, now I've just, let me try it again. Two four nine six one. 24961. Two four nine seven eight. 24978. 24978. 250045. 25005. Okay, so we've got 4 measurements here, and we're going to take the average of them and see what happens. So 2.5007, 2.4978, 2.4988, 2.505. So the average is 2.49945. So that's very close. So that's 1/100th of a millimeter, 0.014 millimeters, or half a thousandth. Or from 2.5. So I strongly suspect that the original specification was 2.5 for this thing and 2.501 or 2.502 for the shaft. And that makes sense. So let's do the other side. roughly guesstimating 45 degrees, but one has to ask how much difference it's going to make. Okay, so that's the vertical. 2.501. Two point five double O 1 5. 2.5 003. Okay. 2.4995. 2.4999. 2.4999. And this way. 2.4999. That's not good. 2.49895. 2.4989. 2.4991. 2.4991. Okay, 2.4991. 2.5011 plus 2.53. 2.5011, 2.5003, 2.4999, 2.4991, divided 4 equals 2.5001 plus 2.4995. Okay, so the right-hand side is 2.5001 if you average for all four measurements. The left-hand side is 2.49945. The average of the two is 2.499775, which is 2 thousandths off from 2.5, which is 0.005, which is basically 6 microns off from 2.5 inches. Microns being a thousandth of a millimeter, you Americans. Okay, microns. And this basically means that we can bank on these measurements being 2.5 inches exactly. So they have brought this out to exactly 2.5 inches. We can bank on that. But because our smallest measurement of all of them is 2.4988, which is 1.2 thousandths smaller than the nominal measurements of 2.5. That's the smallest measurement I have here, all of these, which is the maximum distortion, so it's 1.2. So basically, our interference, if we machine this to 2.501, it's going to be 1 thousandths plus 1.2 thousandths because of the ovalness. That gives a total of 2.2 thousandths. Okay? Now, what is the difference in temperature that we need in order to get 2.2 thousandths? Well, that's easy to work out. So, according to Shigley, if I look in the index, we've got some thermal expansion coefficients here. And you can see that carbon steel and cast iron are both about 10 to the minus 6. Sorry, 10 times 10 to the minus 6. So if we bank on 10 times 10 to the minus 6, so E6 minus 10E minus, stupid calculator doesn't do negative exponents. 10E6 minus, oh, there it is. So there, so we've got 2.5 inches times 2.5 times 25.4 equals, so each degree centigrade gives you 0.6 microns, so .061 divided by so we need 96 degrees centigrade difference in order to make up 0.06 millimeters difference. And that seems fine to me. Okay, now the interference, I mean, you know, that if you only have 100 degrees centigrade, so it's basically 100 degrees centigrade difference. Now, of course, I know from experience that you need an extra thousandths, or you need extra thousandths of an inch, even up over and above a zero interference fit in order for them to slide together. A zero interference fit actually has to be pressed. It doesn't actually slide in. A slip fit is actually a slide clearance. So let's say we need an extra thousandths. So equals 8.2. 12. That doesn't make sense. 0.081 and 10, 3, 6 times 4 times 2.5 equals store A. So 0.081 divide. So we'll probably need as high as 170 degrees, 127, degrees. Let's say 130 degrees difference. So, so 130 degrees Fahrenheit is 266 degrees. So 130 degrees Celsius, 266 degrees Fahrenheit, and it's about 100 degrees in my, well, it can be as high as 100 degrees in my garage. So that's 370 degrees Fahrenheit. Okay. Now this oven for cooking goes up to 400 degrees Fahrenheit or something, 350. And then if we take the tubes and cool them with dry ice, just find out what is the temperature of dry ice. So dry ice is minus 100 degrees Fahrenheit. So we should easily be able to get our 130 degrees Celsius different, because minus 100 degrees Fahrenheit, I mean that's minus 78 degrees C is, so if we add 30 to that, so it's 78 plus 30 plus 100 degrees. So let's say we heat this to 130 degrees. We should easily get, it's easy to achieve, let's put it that way. So all we've got to do is get some dry ice, and with the dry ice we should be able to fit these quite easily. That's all that there really is. So that's the plan. We're going to put the tubes in dry ice. We're going to heat these up with a blowtorch. I don't have an acetylene blowtorch, so I'll just use a regular gas one. And between the two, we should have the temperature that we need. So that's all there is to it. So the only thing left is to measure this thing, and hopefully there's not a huge difference in their design that they would have made this You know, would it be really ridiculous if they'd made this different? So let's see. .5016. 2.5018. No, 2.958. So this is a very polished surface on the inside, whereas the other one has machine marks. I don't know why that is. So I think this also isn't round, so I'm going to have to go through the whole process of measuring this again. can't believe that one. Two point four nine five, 2.4953. Okay. So this seems like it's 2.495. Which is 5 thousandths under, which is a lot. And that's very, very strange. That's pretty consistent, 2.495. It's 5 thousandths under. I just can't understand why I seem to get that reading that I got. No, I mean it's definitely 5 thousandths under, so this is really much smaller than the other one, and then of course I'm going to have to take that into account when I machine this. So, I mean, I don't know what the other side is. So this is the driver's side, and 2.495. It's the same thing. Same story. Turn it this way. Two point four nine. 2.494. .496. Okay, so there's no question that this is, it's 4 to 5 thou smaller than 2.5 inches. So that means that the bottom line is the actual tubes, the inside, must be machined to 2/1000 over, and the outside of the axle tube, the part that goes into the seat bracket, must be machined to oh wait, no, that's plus 1000, sorry. That's plus 1000. So this must be machined to plus 1000th over, and this must be machined to 3/1000 under. Okay. Minus 3/1000 plus. So in order to have 1/1000 clearance, you're going to have to machine for here 3/1000 under, so that it's 1/1000 larger. I don't even know what I'm saying anymore. Yes, actually 3/1000 is correct, because we want a tighter fit for the steel than we do for the cast iron. Okay, so, and we can do that because this is round. Okay, but this is not round. So 1/1000 for here and 3/1000 and 2/1000 for here, which means that we need these 3/1000 under, because this is 2.595. So this is, so that will make sense. And so that's very important, because obviously once I've pressed in these sides, and I'm going to press these in first, and then I discover the other one doesn't fit, that could be a real problem. Now obviously to test it first, I'm going to take a small piece of tube and I'm going to machine it to what I think this measures out to, and see if it just slips in there. And if it does, then we've confirmed our measurements. So that's the story.